everyone, and welcome to my Roblox scripting series where I teach you how to script on Roblox. In this video, I'm going to show you everything you need to know about C-frame values. So C-frames are short for coordinate frames, which are values that contain positional and rotational data. C-frames require the understanding of vector 3 values, so if you haven't watched my previous video, please watch that first. The link is in the description. So C-frames, just like vector 3s, deal with 3D objects in space, but they have much more functionality and appeal to a greater number of use cases in games. To make this so, C-frames were made up of 3 positional coordinates, just like the vector 3, and then 9 more numerical values that make up a 3x3 matrix. This matrix represents the rotation data of the part. You can create a new C-frame by using a number of constructors, .new, .angles, .lookat, and more. There are a number of ways you can use the .new function to create a C-frame. You can use it as if it was a regular vector 3 and it will give you a C-frame with position data with no rotation data. You can use it with one vector 3 as an argument, which does the same thing. You can use it with 2 vector 3s, the first being the position the part will be at and the second being the position the part faces towards. And you can also just have no arguments, which will return a C-frame with no position or rotation, meaning a position at the origin and a standard rotation of 0 radians. Now CFrame.angles gives you a C-frame but with no position data. It takes 3 arguments, an x, y, and z, and they are all numbers that represent the rotation on each axis. The rotations are in radians, so if you want to see how many degrees of rotation there are, you can write them like this, where you input the number of degrees and the computer will convert them to radians. Now CFrame.lookat does the same thing as the .new function that takes 2 vector 3s but has an additional third argument, a vector 3 which specifies the up vector of the C-frame. And an even deeper version of this function would be the .fromMatrix function, which takes 3 required arguments and 1 optional argument. The first argument is the position the part will be at. The second argument is the position that its x-axis will be facing. The third argument is the position that the y-axis will be facing. And the last argument will be the same, but for the z-axis. If there is no fourth argument, the z-axis will be calculated as the axis that is perpendicular to both the x and y axes. Now once a C-frame is created, you can access certain components of it. If you just want the position data, then you can get the position like this, which is just a vector 3. If you want the rotation data, you can get it like this, which will return a C-frame with all the rotation data but with no position data. You can get the x vector, which is the direction to the right relative to the part, either by saying x vector or by saying right vector. They both return the same vector 3. If you want left vectors, you can just make it negative. The same goes for the y vector and the up vector, but the z vector and the look vector point in opposite directions. If you want the forward face, you take the look vector or the negative z vector, and if you want the backwards face, you take the negative look vector or the z vector. You can also directly access the x, y, and z position components just like a vector 3. Now onto the methods. You can lerp between C-frames just like you can with vector 3s. If we lerp between these 2 blue parts that are positioned and rotated differently, we can see that if we lerp halfway, the position will be the midpoint between those 2 parts, and its rotation will be halfway between the rotations of each blue part. Now the getComponents function returns 12 values, the x, y, and z coordinates, and a 3x3 rotation matrix. Next, 2 Euler angles and 2 orientation return 3 values of the x, y, and z axis rotations in radians. And the inverse function returns the inverse C-frame of the C-frame you called it on, which has a good set of applications. Now these next few functions are going to relate to absolute and relative positioning, or more commonly known as world and object space. World space is positioning with respect to the world's axis, which is the absolute x direction, the absolute y direction, and the absolute z direction. Vector 3 values are always with respect to the world's axes. If I want to set this part's position 100 studs above the origin, I would simply make a vector 3 with 100 in the y-axis and then set the part's position to that. I can also do world offsets, where if I want this red part to be 2 studs above this blue part, I can set the red part's position to the blue part's position and add a vector 3 value with 2 on the y-axis. The same goes for a C-frame in certain situations. If I want a part's C-frame to be 2 studs above the origin, I can just do it like this as if it was a vector 3. But offsetting with the C-frame is different. It deals with relative positioning. Now relative positioning is positioning relative to a position that is not the origin and does not use the world's axes. So if I had a part and its relative x-axis was originally aligned with the world's axis, nothing would change. But if I rotate the part, Now its relative x-axis is now different from the world's axis. So in the first scenario, moving this part to its right would be the same as moving its vector 3 world position, but in the second scenario, moving the part to its right would not. It would be moving in the direction of its relative x-axis. This is what makes CFrames useful. So if I wanted to move this red part 2 studs to its right, I would have to use CFrames because I don't know which direction its right face is pointing, and I can't get that through just vector 3's alone. With CFrames, I can do this by getting the x vector of the CFrame, since that represents the direction pointing to its right relative to the part. Now these vectors are unit vectors, meaning their magnitude is 1. So if I want the part to be 2 studs away, I have to multiply that vector by 2. Now, this part is moving 2 studs to its right every time I run this code. If I wanted to move the part to the left, I would just simply multiply the right vector by a negative number. I can do the same going forwards and backwards, and I can do the same going up and down. Now onto the functions. So these next 2 CFrame functions are the ones that return CFrames from world to object space or object to world space. To world space takes an offset CFrame and returns a CFrame relative to the origin that is equivalent. You could also write this as a CFrame multiplied by a CFrame. For example, if I wanted this red part to be 2 studs above the top face of this blue part and also have the same rotation as the blue part, I would set the red part's CFrame to the blue part's CFrame and multiply it by an offset CFrame with a 2 in the y-axis direction relative to the blue part. If we run the game, you can now see that the red part is in the correct spot. Now to object space transforms a CFrame that is relative to the origin and returns that same CFrame but relative to another reference that isn't the origin. So if I wanted to find the offset of this red part from this blue part, I would call the function like this. You can check if you have the right CFrame by taking the magnitude of the offset CFrame's position and seeing if that is roughly equal to the distance between the red part and the blue part. If they're close, then you have the right offset. You could also write this function as the inverse CFrame of the red part multiplied by the CFrame of the blue part. Now point to world space transforms only the positional offset to world space and returns a vector 3 value of that position with respect to the origin. So like in the example with to world space, the red part would be 2 studs above the top face of the blue part, but it wouldn't have the same rotation as the blue part. Point to object space transforms only the positional value of the CFrame from world space and returns a vector 3 of that position relative to another position that is not the origin. This will get the offset without the rotation, while to object space will get the offset with the rotation. Vector to world space takes a CFrame in object space and transforms its rotation into world space, returning a vector 3 representing the direction of that new rotation. It is basically just like point to world space, except that instead of removing the rotational values, it removes the positional values. Vector to object space takes a CFrame in the world space and transforms its rotation into object space, returning a vector 3 representing the offset directional value to another vector. Again, it is basically just like point to object space, except that instead of removing the rotational values, it removes the positional values. There's a lot going on in CFrames, and there are many functions that you can access to manipulate 3D objects. One big application is welding, since that heavily deals with relative positioning. CFrames are a major part of Roblox programming. You should take a bit of time reading other scripts and seeing how they use CFrames. The Roblox documentation also has good examples as well. Link is in the description. Thanks for watching. Please leave a comment on how you felt on the video, and I will see you in the next tutorial.